My name is Eleanor Fadely. I'm a PhD candidate in environmental engineering at UC Davis, and I study the precipitation of manganese oxide minerals by bacteria. Manganese oxides are highly reactive minerals that influence biogeochemical processes, including nutrient cycling and contaminant mobility. They have a particular affinity for toxicant metals, making them an effective tool for soil remediation or water treatment. Manganese oxide precipitation is typically studied either in well-mixed batch systems, which don't account for spatial complexity, or in column scale systems, which don't allow for direct and continuous measurements. In order to study microbial manganese oxide precipitation in environments that are as complex as soils or water treatment filters, we need an experimental platform that allows for in situ and real-time measurements. We've developed microfluidic reactors with a sand grain geometry to simulate porous environments. We use a pressure-based flow control system to sequentially inject fluids to grow bacterial biofilms and to induce manganese oxide precipitation. By combining this system with optical microscopy, we can directly visualize manganese oxide precipitation inside individual pores over time and with high spatial resolution. We observe that manganese oxides first precipitate on biofilm surfaces, but over time, minerals accumulate at the edges of biofilms in contact with pore fluid. If we quantify manganese oxide precipitation over the whole pore space in the longitudinal direction of flow, we see that minerals accumulate preferentially on the inlet side of the reactor pore space near the source of aqueous manganese. If we zoom in, we determine that biofilms in the inlet region are accumulating much more manganese oxide mass than biofilms in the outlet region, and that a substantial fraction of that mass is outside of the original biofilm footprint. We can track the manganese oxide mass accumulation inside and outside of the biofilm footprint as a function of time. We see that mineral precipitation over long timescales is sustained by reactions outside the biofilm footprint. This discovery raises new questions about the exact mechanisms of manganese oxide precipitation and the reactivity of these minerals with environmental contaminants. We are now working on integrating X-ray spectroscopy techniques into our microfluidic system, which will provide novel insights into manganese chemistry at the pore scale. I'm deeply grateful to the ARCS Foundation for making so much of this work possible, and I thank you for your ongoing support.